When we started Merit 3D, we had three major hurdles that additive manufacturing or 3D printing had to overcome to make additive a mass manufacturing possibility. Cost, quality, and scalability. Cost, they have to be inexpensive parts like those of injection molding. Quality, injection molded parts look great. And scalability, many parts very, very quickly. In this video, we're just talking about quality. We have other videos that talk about the cost and the scalability that you can reference. We will also discuss how the current 3D technology compares to traditional manufacturing, mostly done in injection molding today. So for a 3D printing technology, we felt that resin or liquid resin have the most potential for great costs, great quality, and scalability to compete with injection molded parts. Within quality, we identified 4 areas that we're going to be addressing today. So the first is durability or mechanical properties. Will your part hold up mechanically to the purpose of the part? Your second is certifications needed for certain industry. For example, you have UL 94 for burn ratings in the automotive industry, aerospace, and the housing market. You have FDA certifications for food safe parts, metal certifications, medical certifications for areas where the part's going to touch a body. And the third area is surface finish, where you can get surfaces smooth like butter and layer lines you can cover. It's the standard in injection molding, and that is the standard that we need to rise to. The fourth area is dimensional accuracy. Are the critical areas, are they accurate, and can they be repeated at scale? So the first point in quality is durability. Is it tough? When people think of tough plastics, they think of polypropylenes, ABSs, nylons, polycarbonates, filled plastics. All these parts have to be tough. And there are many others, but these are kind of the main ones that offer a lot of toughness. When most people think of 3D printing, they think of FDM because it's the most common. It's a filament extrusion process where layer by layer, the part is built. It's very common in R&D labs, homes, libraries, shops. I love FDM because it's so simple and it has been adopted worldwide. But when we started to go down the route, we needed something that didn't look 3D printed. And it had to be tougher than what we were getting on our current FDM printers. We landed on a liquid resin process. Many times that's generally known as like an SLA LCD process with the best surface finish. We tested every single resin that we could get a hold of, trying to find something that was like a current thermoplastic, those exact properties. Well, our tests were very disappointing. We took parts, not this part, we took parts and we chucked them on the ground. And we wanted to see when they would break. Well, we found nothing that was like ABSs or nylons. We said we needed something better for our mass production parts, and we were told many times that we were about 15 years ahead of our time. Then one day, we received a new test material from Photocentric in the UK. We printed a part, we threw it against the concrete floor, and it didn't break. This is our first indication that properties were improving. This part literally bounced in the air. Because parts printed in resin have isotropic properties, the strength is equal in all directions, similar to injection molded parts. It's very comparable to 3D printed powders, but we believe that some of the new resins that are they're coming out with are actually much stronger than other 3D printing technologies. Just yesterday, I read an article that researchers at the Sandia National Laboratories found a way to improve the mechanical properties of a resin by 3 times. That's awesome. Amazing developments in the resin area. One of the disadvantages in resin is 3D resin is fairly new. They have not been through the test of time like thermoplastics have. Some worry about the UV plastic deteriorating over time, but just like the clear coat on your car, we have seen them go through very tough situations. Accelerated weather tests can be used to simulate time, but they really don't replace it. And applications like medical or aerospace usually require very extensive tests to be put in practice with very good reason. Resin prints are also watertight. You don't have to seal them afterwards. What about chemical resistance? Well, we consider this part of the mechanical properties, and this is on a case by case. But to be honest, resins do not hold up to like a thermoplastic like polypropylene, which is a very amazing chemical resistant plastic. But just like your car clear coat or coatings on pipes, it can withstand salts and other chemicals as needed. One big advantage we love with additive and what we are doing is being able to prototype the exact same part as the mass-produced part. That means there's no guessing on the quality of the prototype compared to the real deal. No guessing at all. If the prototype works, the mass-produced finished product will work also. We call it production. The same material, the same process, the same environment, it's the exact same. This accelerates product development by months, even years, but also gives you the ability to improve a product after you release it. Easily increase wall thicknesses, add radiuses, change material because the process is so adaptive. The quality can be improved so easily. The key though is to not give up. Because one prototype broke, keep trying. Different designs, different materials, different resins, just keep trying. With our sister company, Dustis Technologies, we used to have to say, here, test this prototype, but know that it's an FDM, it's a filament print, and it's weaker than the molded part will be. Well, the tester would bring it back and he said it would break. We said, we know it's just a prototype, it should break. The molded part's going to be stronger. Well, we would cut steel for the part, we would build the molds, and sometimes it didn't fix the problem. It was a design issue, not a material issue. And now that we had a mold that needed serious modifications, we either could or could not make the modifications and had to scrap it. Without molds, there are so many options, but it is new territory. Without molds, you don't have minimums. You can 3D print one part, or you can print 1,000,000 parts. A good practice is to print 100, 1,000, scale up as you need it so you don't have a lot of excess inventory. Then if there are quality issues and you want to improve your design, you don't have months or sometimes years of inventory to work through. The last section under durability here are not only new resins being developed for toughness, but some very cool new developments in composites, carbon fibers, metal coatings for 3D prints. They just continue to improve the durability and the strength of these materials. So the second point on quality is having the right certifications. This area is a weakness in additive manufacturing because the technology is so new. It hasn't been around for centuries like injection molding, which is invented in the 1800s, but it is growing, the additive manufacturing certification part of it. You have medical certifications like biocompatibility for specific implants, prosthetics, surgical guides. Certifications like ISO 10993 is for cytotoxicity or skin safe tests. 3D Systems is a great example here because they've developed implants for bones. Dental resins have been around for many years, filling cavities. They have certifications. And obviously they're going in your mouth for many years, and so they have to be very compatible with your body. Even full sets of dentures are being printed for the gums and actually the teeth as well. So another certification is for FDA or food safe materials. It's growing, but it's still very young in this industry. There's not very many certifications that revolve around that process. Another one is the UL process. UL 94 is for flame retardant properties. So as soon as you start getting into automotive applications or houses, electrical applications, they want those to be very safe for burn ratings. And you just have to make sure that the TSD certification is right for your application. But certifications here are weaker in this area, and it's an area of growth in the 3D application area. The third quality point is aesthetics. We love resins for their surface finish options. These prints have a much higher surface finish straight off the printer than a filament or a powder does today. For most of our customers, aesthetics are key. The part can't look like it's 3D printed. And we agree with our customers. I love it when we go to a trade show and we show them a part and we say, look at this part, how is it made? And they say, it's injection molded. And we're like, boom. We wish you were right, but it's not. We're like, yes. So having the part not look like it's 3D printed is key. And a big part here is design. If you design for additive, that's key. Another weakness today in the resin area are colors. You can get black, gray, amber, clear, white. Those are really common. But to get your vibrant colors like these, it's a little bit harder with resins. You can get them in filaments, but BASF has some options, but they're not as developed today. Another option is we can put on a ceramic coating on like these. With resin, you get one color, and so you can coat it in many different colors. And not any of the options for multi-colors are yet available with resin like they are in FDM today. Most of our customers are coming from the injection molding world, and so they're really coming from a single material mold anyway, so it hasn't been a big issue for most of our customers. Textures. Okay, I come from an injection molding world of plastics, and I know how amazing they look when textures are done correctly. And I know how big of a pain they are to put on mold walls. I love textures in additive manufacturing. They are a hidden gem with so much potential. High quality resin prints can have smooth or they can have textured surfaces. And DFAM, or design for additive, is key when you are designing a part and you want a good texture on it. Literally, with the click of a mouse, you can add any texture to any surface of a part. You can add sandblasted, like a heavier or light texture, carbon fiber patterns, other patterns. You can have A through D finishes of mold finishes. You can add logos, you can add pictures. The sky's the limit with this. Textures just don't make the part look great. They hide any visual defects as well. They even make it so you can print a much faster print and you can save money without sacrificing the quality of a print. Injection molding, you really have to stick with the texture you choose from the beginning. You can't just change it. If you change it, you're sacrificing part thickness and many times very heavy costs if it's even possible to change the thickness at all. But polished finishes, like what you would see in a glass cup or what you would see with safety glasses today, they're not really feasible at a high scale with injection molding today. You can do it, but it's a very low scale. The fourth quality is dimensional accuracy. So when you design a part, you want it to be accurate for the purpose. Injection molding is great for this and can hold very tight tolerances. Since it was invented in the 1800s, it's been consistently improved over the years for accuracy. 3D printing is obviously new, and because the 3D printing process is a layer by layer, a growing process, it's more prone to deviations. So the question is, what are the tolerances for your part? What does it require that your tolerances hold? Design is critical for holding dimensional tolerances in 3D. With a good design, we can hold tolerances down to 30, 70 microns. A part not designed for additive may never hold the needed tolerances or may be embarrassing to look at when it comes off the printer. Resin, the machine, your design, many other factors play into this. Large prints are harder to hold very tight tolerances if the tolerance is needed. Like any manufacturing process, quality inspections can be done per batch or at 100%, or sometimes they require just visual inspections. The important thing here is to identify what areas are critical and design for those features. This particular part is a gas mixing nozzle. The internal threads right here are very important to the customer. And the internal channels inside of this, but the OD here really isn't important right here. And so you can have some variations and each part will vary just a little bit. So depending on your tolerances, what you need. If you need an in-depth quality inspection, then different scanning techniques can be used, like a CT or ultrasound. Quality tracking serialization is possible with 3D, as the whole process can be digitized and every part labeled before the printing process. The fifth point in quality is sustainability and quality to our planet. A good design will minimize the waste in a part. We're building layer by layer so we can minimize the material used in the creation of a part. Design it lighter and with less material. So like this pen, it uses lattices to reduce material. And this is the lowest waste possible pen we designed in that effort. So we have a mission to use sustainable materials. We want to help the environment. We need to make parts from sustainable materials like this bio-based resin made from pine or sage. So the end of this is, how does the part get recycled? How does it decompose when it's in our landfills? And what is the end useful life after the end useful life of a part is complete? I hope you enjoyed this video on how we envision 3D quality for 3D printed parts. The quality options are growing so fast, and we are becoming an option for mass production in the 3D world. We make mass production happen in 3D, and if you need a quote, I need a level. If you have any questions, feel free to reach out to us, and let's see if we can make it happen. Thanks.